Greetings again, one and all. Welcome to another exciting video where yet again we're going to be talking through differentiation. However, today things are going to get real because we're going to be looking at the applications of differentiation, in particular second order derivatives, and investigating the nature of stationary points. When the gradient's zero, is it going to be a maximum, a minimum, or something else altogether? So let's get started with, you know what, the 4 quintessential warm-ups. So here are the warm-up questions. You know the drill by now. Try them yourselves, pause the video and have a go. Play the video yet again when you want to have a go and see if you've got them correct. So here they are, and without further ado, let's have a look at the solutions. So question 1, you've got this curve y equals x cubed minus 4x squared plus 4x minus 1. First of all, let's find the gradient function dy by dx. Now, as you should know by now, what we do is you take each term individually, bring the power down to the front if it's a variable, in this case x. So this x cubed becomes 3, and the power of x drops by 1 to x squared. This term here, the 2 comes to the front, multiplies the 4 to give us 8. The power of x drops from a squared to just power 1, and the 4x just becomes plus 4. Any constant terms just stay completely eliminated, so the minus 1 disappears, so we just get left with 3x squared minus 8x plus 4. The second order derivative, we just differentiate dy by dx yet again. And so if we now differentiate this function here, 3x squared becomes 6x, minus 8x becomes minus 8, and the constant term plus 4 vanishes. And so we now get 6x minus 8. We could go again and get the third order derivative, which would be 6. The fourth order derivative would be 0, but you get the idea. Question 2. So using our answer to question 1 part A, find the values of x where the gradient of c is equal to 0. And so what we can realize from this is that the gradient is going to equal 0 when the gradient function is equal to 0. So the gradient is going to be 0 when dy by dx equals 0. Hopefully that's quite obvious. So now, if we just go back to question 1a and remind ourselves what dy by dx was, it was this. So we can set this equal to 0 and solve. So we have 3x squared minus 8x plus 4 equal to 0. Now at this point, if you're really wanting to, you could even use your class whiz and just bang it in and get the 2 different values of x where this function is equal to 0. But just in case an examiner asks you a question along the lines of prove that or show that, it's always handy to remember the bare algebra skills which we'll need. So let's just do this algebraically, just preparing for the eventuality that the examiner doesn't give you the option to use your calculator. So we can partition this minus 8x term by thinking 3 times 4 is 12, and so we need to think of 2 numbers which multiply to 12 but sum to minus 8. So those 2 numbers would be minus 6 and minus 2. So we can now say that we have 3x squared minus 6x minus 2x plus 4 equals 0. This can now factorize. We can factorize from here a 3x, which gives us x minus 2. And the minus 2x plus 4, we can factorize a minus 2 out of that, and again get x minus 2 equal to 0. We can now put the 3x and the minus 2 into their own brackets. As so. Therefore, we can see that the gradient will equal 0 when either x is 2/3 from this bracket, or when x equals 2 from the second bracket. And so I have 2 values of x which will yield a gradient of 0. Question 3, we need to substitute the answers from question 2 just into the second order derivative from question 1 part B. So from question 1 part B, we had d squared y over dx squared. The second order derivative was 6x minus 8. And so our two values from before were x being 2/3 and x being 2. And so we can compute this second order derivative for when x is 1/3. So when x is, whoops, my apologies, not 1/3, it was 2/3, wasn't it? Almost made yet another blunder, infamously. Yes, just going back here, we had 2/3 or 2, my mistake. So when x is 2/3, the second order derivative will be 6 times 2/3 minus 8, which would give us -4. Or, of course, at x being 2, the second order derivative, f double dashed of 2, this, by the way, just to clarify from last time, this is the same notation as this here, just a different way of writing effectively the same thing. So when x is 2, we'd have 6 times 2 minus 8, which would give us 4. And so when x is 2/3, the second order derivative is -4. When x is 2, the second order derivative is +4. Lastly, for the warm-up, we've got here a quadrilateral OABC, and we're told their position vectors OA, OB, and OC. And so O we can define as just being the origin, so sketched on these axes here, and if we do a fairly accurate sketch, this will help us to solve the question. And so relative from O, A is 3 in the I direction, which is along, and then 1 in the J direction. So remember, I and J have the same directions as X and Y on the Cartesian coordinate grid. And so 3 along and 1 up would be very roughly, let's say, here. And so we can label this A. OB is 4I plus 4J. And so imagine going 4 along and 4 up. This would be about here. And so that's B. And C is -2I plus 2J. And so this would be maybe something like this. And that would be C. So why bother doing a sketch? Why do it this way? Well, if you bear in mind what we want to show, we're trying to prove that OABC is a trapezium. So to prove that something is a trapezium, we just need one main thing. All we need for a trapezium is to prove that we've got one pair of parallel sides in the quadrilateral. Okay, so if we look here, we can use this accurate-ish sketch. If we were to just draw out OABC, so let's just draw this from O to A to B, B to C, and back down to O. We can see that the sides we can prove which are parallel just by sketching out fairly accurately. We need to prove that these two sides are parallel if we can, and if we do, that's shown that this quadrilateral is a trapezium. And so let's just consider CB. So the position vector from C to B. So how can we get from C to B using the vectors we know? Well, what we could do is we could go from C to O, and then we could go from O to B. So CB is the same as going from C to O, and then from O to B. I can't just say what CB is, because we're not given any vector here that relates C and B together. However, from C to O, we're told what OC is, and so this is from C to O is going to be the opposite way round of O to C, and then just plus OB. And so we're told what OC is, and so from O to C is -2I plus 2J. And so minus OC is minus 2I plus 2J. And then OB, we are told OB is 4I plus 4J. So we can just add on 4i plus 4j. Add a bit of colour coding as well. I think CO feels slightly left out. In fact, no, I won't colour that part of it in. I'll colour this part in. There we go. So if we just simplify this down, so minus 2i is positive 2i minus 2j plus 4i plus 4j. Regroup the terms. 2i plus 4i gives us 6i. Minus 2j plus 4j gives us 2j. Now we can factorise out a 2 from this. We get 2 lots of 3i plus j. But if we return to how these position vectors were derived, how we set them out to be, 3i plus j, if you notice, is actually OA. And so this is the same as saying it's 2 lots of a position vector from O to A. So what we've done here is we've proved that CB is a multiple of OA. Okay, so if I just put CB like this, we've proved that this vector here is a multiple of this vector here. Now you need to remember from before, when we did the topic of vectors, that if we can prove that one vector is a multiple of the other, that those 2 vectors are parallel to each other. So the next line of logic says, therefore, CB is parallel to OA, and because CB and OA are both sides of this parallelogram, this therefore implies and proves that the parallelogram OABC must be a trapezium. And that's the warm-up questions completed. So we can move on to the main course now. Okay, so what we need to look at here is stationary points. So I need to just define with you what a stationary point is. So in plain English, if you've got a curve, a stationary point is just any point on that curve where the gradient is 0. Okay, so any point where the gradient is equal to 0. And so we can actually work out the nature of stationary points, because some stationary points will be a maximum, some will be a minimum, and some will be what's called a point of inflection. I'll talk you through that point of inflection in a bit more depth later on. So let's just have a look at this step-by-step guide, which I'll talk through with you and explain. So, first of all, we locate the x-coordinate of each stationary point by just working out the gradient function and then solving that. So setting the gradient function equal to 0 and working out what values of x yield a gradient of 0. The second step is for each of those x-coordinates, we're going to just think about 2 points very, very close to the value of x, which gives a gradient of 0, either side of where x gives a gradient of 0. What this will do, if you think about 2 points very close either side of where the gradient is 0, we can think about what's happening around that point. So for example here, if I had a local maximum, what would happen is, if we worked out the gradient was 0 and we had a stationary point, then just before that point the gradient would be positive, and just after the gradient would be negative. And so if I just show you a local maximum, just very roughly sketched out. Okay, so imagine this is our local maximum, LM, just to be, actually I'll call it Lmax. So imagine this is the maximum. Then obviously coming up this way, we have a positive gradient equal to 0 there, and then afterwards the gradient becomes negative. And so that's just an illustration to show you what a maximum looks like. Positive gradient, 0, negative gradient. And understandably, a local minimum is the complete opposite way round. So a local minimum, if we call this L min, whoops, I'll just get that into a black font rather than red. So call this L min, and imagine this being the minimum point. Then reading left to right, what we'd have here is initially a negative gradient as it's going down, comes to a 0 gradient, then after the minimum it starts going up. Hence a local minimum has negative gradient, 0 gradient, and then positive. The points of inflection, don't worry about these too much. I'm going to explain these in a bit more depth in just a second or so. So just try a bit more information on this. Here's a sketch showing the 3 main points. So as I've just sketched out for you, a maximum is like this. Positive gradient, then 0, then negative. A minimum is where we have negative gradient, 0, then positive. And a point of inflection is where we have the same sign of gradient at both sides. So it could be negative, 0, negative, or it could have been positive, 0, and then positive as well. And so a point of inflection is where the gradient's 0, but either side of that critical point, the gradient is the same sign. So the gradient doesn't actually change sign from positive to negative or vice versa. It stays the same sign. So points of inflection are quite a strange concept, but I'm going to give you a visual representation of them, which will hopefully make a bit more sense. So for now, we've got this function here, and we want to find the coordinates of any stationary points and to determine the nature of those points. So let's have a look at this one together. So what we'd have is, first of all, we need to work out the gradient function of this. And the gradient function of this we can actually compute by just doing dy by dx. However, just think about warm-up question 1. Okay, so if we were to do dy by dx, we'd get 3x squared minus 8x plus 4. I'm not going to go any further right now. Just think about warm-up question 1 if you can, and if you want to, just refer to warm-up question 1 now. So have you done that? Had a look at warm-up question 1? If not, I'm just going to say it. Warm-up question 1 links directly to this question. So I'm just going to skip ahead for those of you that have seen it and understood the link. So imagine this finished off, and we'd get what we had from warm-up question 1. Only this time, instead of just working out where the gradient's 0, we're using the term stationary points, which is one and the same thing. Where the gradient is 0, that's when saying the stationary points are happening. Stationary points are when dy by dx equals 0. And so like in warm-up question 1, we should have seen that the stationary points, solving this, are when x is either 2/3 or where x is equal to 2. So now what we can do is we can think of each point here individually. So let's think about the stationary point where x is 2/3. So the stationary point where x is 2/3. By the way, of course, it did say to find the coordinates, and so to make sure we don't forget to find the y value, let's just find the coordinates here first. So when x is 2/3, we'd have that y is 2/3 cubed minus 4 lots of 2 cubed squared plus 4 lots of 2 cubed minus 1 So if we use our trusted calculators to do this for us, the class whiz, of course, and so we have 2 over 3 to the power 3. Come on, hurry up. There we go. Minus 4 lots of 2 cubed squared plus 4 lots of 2 cubed minus 1. And we get 5 over 27. So where x is 2/3, that's a coordinate 2/3 and 5/27, just to make sure we're answering the question. So what we can do here is we can take 2 points very close either side of where x is 2/3. Now you should hopefully know well by now that 2/3 as a decimal is about 0.66666, and so we can try working out the gradient just before that. So instead of 0.6666, let's go for where x is 0.65. And so when x is 0.65, let's compute the gradient for that point. So we'd have 3 lots of 0.65 squared. Oh, of course, by the way, I best just mention, you don't have to go for 0.65. You could have put 0.66, 0.64, as long as it's very close to 2/3, but just less than 2/3. There's no exact number you have to go for. So if you're thinking, where's he got 0.65 from? It didn't have to be that. As long as it's minutely less than 2/3, you're going to be fine. Anyway, carrying on. So 3 lots of 0.65 squared minus 8 lots of 0.65 plus 4. So unless I'm mistaken, that is 27 over 400. Which, the main thing is, that's a positive value. Now we take a point just after 0.66666. So let's try evaluating the gradient at 0.67. So again, use your calculator for this, obviously. So we get 3 lots of 0.67 squared minus 8 lots of 0.67 plus 4, unless my earlier calculations are mistaken, that should come out as minus 133 over 10,000. Now the exact value doesn't matter. All we're really concerned about here is the sign of our answer. This is negative, and so just make a note that's negative. And so this gradient has gone from being positive, then to 0, and then to a negative value. So positive, 0, negative, just return to what we had before. If it's positive, 0, negative, that shows that it must be a local maximum. So therefore, what we've proven here is the point 2/3 and 5/27 is a local maximum. If you're thinking this is quite an arduous process, don't worry, there is a much simpler way I can show you and will show you later on. So that's a local maximum. Now we're going to do a similar idea for the second stationary point, which is where x is equal to 2. So if I just scroll down here and have a look at this one. And again, don't forget, we need to work out the actual coordinate here as well. And so let's think about the stationary point. Where x is 2. And then also let's compute the value of y for when x is 2. And that's gone sort of over the line. There we go. So when x is 2, we need to work out the value of y. So let's do this now. So we'd get 2 cubed which is 8 minus 4 times 2 squared, so minus 4 times 4, plus 4 times 2, which is 8, minus 1, we get minus 1. So we just need to pick two values either side of when x is 2. So what I'd suggest doing would be picking 1.99 and 2.01 and evaluating the gradient at those 2 points. So let's try when x is 1.99 and working out the gradient there. So when x is 1.99, the gradient function would be 3 lots of 1.99 squared minus 8 lots of 1.99, and then we'd have plus 4, because we have plus 4 here. And again, unless my previous calculations were mistaken, that gives us minus 397 over 10,000. Yet again, don't let the actual value worry you. The main thing is just considering if that value is positive or negative, and of course this is a negative value, so that's minus. Whereas when we try the gradient function at 2.01, what we get here is 3 lots of 2.01 squared minus 8 lots of 2.01 plus 4, and that should give us 403 over 10,000. Yet again, can't stress enough, don't get hung up on the actual value, just consider, is it positive, is it negative, and of course this is a positive value. So this time we can see the gradient's gone from being negative when we have 1.99 down to 0 when we have x being 2, and then to 403 over 10,000 to a positive value when x is 2.01. And so if we just go back and think about what sort of stationary point we have if it goes from negative, 0, positive, in this instance, from negative to 0 to positive, that proves we have a local minimum point. Whoops, gone too far. So therefore we can say that for point 2 minus 1 is a local minimum. Now I gave the game away by going a bit too far onto the next slide, but what I would say, if you're working from home or you're working independently, to use the power of technology to your advantage. I've mentioned before quite a few times the brilliant tool Desmos.com, where you can do some online graphing very quickly and intuitively with a very easy interface to get your head around. And so from Desmos, if we just verify our results by typing in and trying for ourselves, we actually end up with this graph here, which is the actual graph of the function. And as you can see, this is where x is 2/3, and this awkward decimal is 5/27. And as you can see, this is a local maximum point. And the point where we have x being 2, y being minus 1, that's a local minimum. If you're caught up about, well, why is it a local minimum? Why not just a maximum or minimum? It's because if you have different functions, there could be more than one minimum or maximum. So for example, for a different function, it might be coming down here, and that could be a second local maximum. It's not the case of this graph, but hopefully you see that it doesn't necessarily just have to be limited to one minimum, one maximum point. So Desmos can just prove that your calculations are correct and put your mind at ease. So always use Desmos if you can, would be my suggestion. So going back to this idea of a point of inflection. Local minimum is when it's a happy parabola, the bottom of that. Local maximum, where you've got a sad parabola, the vertex of that. And this thing here, like an S shape or an inverted S, is a point of inflection. Now, I did say I'd try and give a bit more flavour, a bit more sort of background as to what a point of inflection means. The best way I can picture it is the point of inflection where we have a 0 gradient. It's where two bits of a curve are joined together, where the two bits that join are curving in the opposite direction. So if you look here, To the left, the curve is curving downwards. Afterwards, it's curving upwards. And so from my point of view, inside my head, it's where there's a change of curvature in the curve, but not a change in the sign of the gradient. So that's just one example. I'm going to give you another 3 to have a look at. So we'll just mention this in a second, what I've got here. First of all, it's going back to the points of inflection. And so that's a point of inflection there, curving down, then curving up. This is another one. There'd be the point of inflection. That's curving down and then curving up. And this one here, that would be a point of inflection. That's where it could be curving down there and curving up. So a point of inflection, hopefully I want you to see here, doesn't actually necessarily mean that it's got a gradient of 0 either. So points of inflection are weird things. It could be where the gradient is 0. It could also be where the gradient isn't 0. Obviously here you can see the gradient of a point of inflection, that tangent would be going downwards. This would be going downwards too. So what's this stuff at the top here? Well, I did mention earlier there's an easier way of doing this in some cases. So this is to take the second order derivative. So the derivative of a function tells you the gradient at any particular point on the curve. And the gradient is the rate of change of that function. The second order derivative gives you the rate of change of the rate of change, which means the rate of change of the gradient itself. So, if a second order derivative at the point where x is a stationary point, if a second order derivative at that point is greater than 0, that shows us that that point must be a local minimum. Okay, so when the gradient is changing in the positive direction, where the gradient is growing, that must be a local minimum, which might be counterintuitive. So that means when the gradient is getting bigger, the point will be a minimum. If I just take you back to a previous graph here, I want you to imagine it this way. If it's a local minimum, just imagine me writing the gradient at different points. So there, the gradient's very negative, isn't it? Let's say it's -8. A bit less steep, say -6, -4, -2, then the gradient is 0. After this point, the gradient's getting positive. So 2, 4, 6, 8. So reading left to right, you can see the gradient is getting bigger each time. So as the gradient's increasing, when the rate of change of the gradient is positive, that's a local minimum. And the complete reverse here. So if the rate of change of gradient is negative, when the gradient is decreasing each time, that's consistent with it being a local maximum. The way to think of this is, if the rate of the gradient is decreasing, then it's reached its absolute maximum point, because it's only going to be downhill from there on. Likewise for a local minimum. However, when we have the second order derivative equal to 0, then that doesn't tell us anything at all really. It just tells us that it could be a local maximum, a local minimum, or a point of inflection. So a common mistake here is to remember these two things at the top. When the second order derivative is positive at the point where we have a stationary point on the curve, it's a local minimum. Where it's negative, it's a local maximum. Most people remember those two, and then just wrongly assume if it's not a minimum or maximum, the other one here, when it's equal to 0, that must be a point of inflection. It doesn't necessarily mean that. A point of inflection is a point, as I say, where the direction of a curve changes without the gradient itself changing sign. So to evaluate when f dashed a is equal to 0, to work out what that is, the only way we can do that when f dashed of a equals to 0, the only way of working out what that is is by doing that first method, by examining the gradient at 2 points either side of A, which we did earlier. Otherwise, there's no telling what sort of stationary point that could be, if indeed it's a stationary point at all. That was a bit of a mouthful, wasn't it? So it'll help if I give you a couple of extra works examples to get your head around. So question 1 part A of this next batch of worked examples. We've got here this function, y equals 2x cubed minus 15x squared plus 24x plus 6. And we need to find the coordinates of the stationary points on that curve. And so what we need to do first of all for part A is to find the gradient function dy by dx. So dy by dx, 2x cubed, the 3 comes to the front and multiplies a 2, so we get 6, and the power of x drops by 1, so cubed becomes squared. The minus 15x squared, the 2 comes to the front, multiplies a 15 to give us 30, the power of x drops from 2 to 1, plus 24x just becomes 24, the x effectively vanishes, and the constant term 6 vanishes altogether. And so we have 6x squared minus 30x plus 24. If we're trying to find stationary points, then we know by now stationary points are when the gradient is equal to 0. So we can just write that down, stationary points when dy by dx equals 0. So we set this quadratic equal to 0 and solve. So we have 6x squared minus 30x plus 24 equals 0. And again, you can just do this on your class whiz if you so wish, but I'm just going to show you how to do it algebraically in case the examiner so chooses to word the question where you're stopped from just using your calculator. So from an understanding point of view, let's solve this. Look at these numbers here, the coefficients of x squared and x and the constant. We can divide through by 6. That gives us x squared minus 5x plus 4 equal to 0. We can then easily factorise this. We'd have x minus 4, x minus 1 equal to 0. Therefore, we've got stationary points when x is 1 and when x is 4. So 2 different stationary points. For part B, we now use the second derivative to determine the nature of these stationary points. So for part B, let's just pick when x is 1 first. So let's pick when x is 1. Also as well, what we'll need to do is we need to find the second order derivative. And so the second order derivative, d squared y over dx squared, we differentiate this again, we get 12x minus 30. So we're going to use this for both stationary points. Just thinking as well, being a bit absent-minded here, for part A it did say find the coordinates of the stationary points, not just the values for x. And so if we just put a freeze on part B for a moment, if I return and actually finish off part A as I should have done initially, we need to work out the y coordinate when x is 1. So when x is 1, y is going to equal 2 lots of 1 cubed minus 15 lots of 1 squared plus 24 lots of 1 plus 6, which is 17. And so one set of coordinates is when x is 1 and y is 17, and also when x is 4, just substituting this into the initial function, we get y equals 2 lots of 4 cubed minus 15 lots of 4 squared plus 24 lots of 4 plus 6. And that, if you try it in your calculator, will give you minus 10. So the coordinates of the stationary points, as we were asked actually, the coordinates of the stationary points. My writing's getting worse, I apologise. Stationary points are 1 and 17 and 4 minus 10. So they're the two sets of coordinates where we have the stationary points. Now we can finally have a look properly at part B. So let's just extend this line here to separate part A from part B. There we go. So like I was saying for part B, so let's just think about the nature of each point individually. So when x is 1, we need to use the second derivative, which is 12x minus 30. So f double dashed of 1 is going to be 12 lots of 1 minus 30, which is going to be 12 minus 30, which is minus 18, which is obviously less than 0. So just returning to what we had from before, when we evaluate the gradient for second order derivative and we get a value which is less than 0, that denotes a local maximum. So that tells us that when x is 1, we have a local maximum. So that means when 117 is a local maximum. And then we're going to try when x is equal to 4 and see what happens there. So when x is equal to 4, and evaluate the second order derivative for 4, we have 12 lots of 4 minus 30. 12 lots of 4 is 48, minus 30 is 18, and obviously that's greater than 0. And so because the second order derivative at the stationary point here yields a value greater than 0, that shows us that we must have a local minimum at this point. So therefore, the point 4 and minus 10 has to be a local minimum. Yet again, just to show you the power of Desmos, if you were to input this function into Desmos and just verify your results, you can also use GeoGebra as well, which apparently is just as good. I don't quite get GeoGebra, but each to their own. I'm sure both are great tools. You should find that the function is looking a bit like this. And so there's 117, which is the maximum, as you can see. And then down here, 4 minus 10, that's the local minimum, as we said as well. So that just validates what we had using the algebraic methods. Lastly, question 2, we've got this curve here, y equals 1 over x plus 27x cubed, has stationary points where x is plus or minus some constant a. So for part A, we need to find the value of this constant. So for part A, we need to find the gradient function. So what I'd suggest doing first of all, actually, come to think of it, is just rewriting this in a slightly nicer form. 1 over x is x to the power minus 1. When we rewrite them as an index form, it just makes it much easier to differentiate. So dy by dx, bring the minus 1 to the front. We have minus x to the power minus 2. Bring the 3 to the front. 27 times 3 is 81. 81x squared. So we want to find the stationary points. So this is going to be a stationary point when the gradient function is equal to 0. So we can just save that here. So stationary points are when this is going to be equal to 0. So minus x minus 2 plus 81x squared equal to 0. This is a bit of a weird one to solve. This isn't an equation type you see very often. What I'd suggest doing is just multiplying everything by x squared. So if we multiply both sides here by x squared, x to the power minus 2 multiplied by x to the power 2 will give us x to the power 0. So this thing here will just change to minus 1. And this here, 81x squared times another x squared, gives us 81x to the power 4. So this is actually a difference of 2 squares. We can say this is 9x squared plus 1, 9x squared minus 1 equals 0. So one of these brackets needs to equal 0 to solve what we need to solve. If we look here, for this bracket to equal 0, 9x squared would have to equal minus 1. But something squared can never be negative, so we've got no solutions here. So that's going to yield no solutions. So all our solutions are hidden within this bracket here. So we can therefore say that 9x squared equals 1. So therefore x is going to be plus or minus the square root of a ninth, which is plus or minus 1/3. Now the original question for part A was to find this value a, so therefore a must be 1/3. So scrolling back up, now I've got a is 1/3. We need to sketch the graph of this curve. Okay, so what I'd suggest we do is find the coordinates of these stationary points. So let's just think about when x is minus 1/3, what y would be. So y would be 1 over minus 1/3 plus 27 lots of minus 1/3 to the power 3. So God knows what this is, let's just see. So 1 over minus 1/3 plus 27 lots of minus 1/3 all cubed. That gives us minus 4. So therefore, minus 1/3 minus 4 is a stationary point. In the same way, let's see what happens when x is 1/3. So when x is 1/3, we have y is 1 over 1/3 plus 27 lots of 1/3 cubed. And that would give you not minus 4, but positive 4. So the other stationary point is 1/3 4. So now we can begin to build our sketch. So we've got the coordinates of our stationary points. So let's just fill in an x and y axis. So we have a minimum at 1/3 and 4. Let's just sketch it in there. And a minimum at minus 1/3, minus 4. Let's just pop it in here. That's minus a third. Ah, damn. Silly me, it's not minus a third, I mean to say minus 4. Almost another silly mistake. So that's minus 4. That's positive 4. This is minus a third. Over here is positive a third. Now, just remember the actual function. The function included a 1 over x part. So if you just scroll up for a second, look, we have 1 over x. Now just remember, as x gets closer and closer to 0, as x gets closer and closer to the origin, this is going to move closer and closer to 1 divided by a tiny, tiny, tiny value. So it's going to go towards infinity on the positive side of x, and this is going to go towards negative infinity on the minus side of the x-axis. This is called an asymptote, if you remember. So where x becomes 0, we're going to have an asymptote. And so the line x equals 0 is going to be something which can't actually be touched by the curve. And so just to sketch this out, what we'd have when it becomes bigger over here, x, the x cubed part will start to dominate. And so it's going to go bigger after here. However, let's curve it up slightly, when x gets closer and closer to 0, the 1 over x term is going to make the function shoot up towards infinity. So we're going to have something like this. We're also going to have something similar at the other end as well. This is going to be a local maximum. So what's going to happen is it's going to curve down like this, but as it gets closer towards the y-axis, this is going to get closer and closer asymptotically to the y-axis. So once again, just to go back to my point about Desmos, if we just try this on Desmos, you should get something that looks a bit like this. And again, that's 1/3 4. This is minus a third, minus 4. And that obviously blows my terrible sketch away, but you can see that my sketch, in terms of its idea, wasn't a million miles off. So it just takes practice to get good at sketches and to get used to sketching out what the question is asking you to. Okay, so this is quite a huge concept here. So really important as ever, but particularly today, that you try these suggested exercises on page 276. So try exercise 12i, page 276, as a bare minimum, try question 3 and then question 5, 6 and 7. I would encourage you to try the whole exercise based on the importance of this concept with the second order derivative. But try those, please. If you have any problems, please do email me or leave a comment in the comments section. I'll get back to you as soon as I reasonably can do. Okay, so thanks for listening, keep safe, and until next time, I'll see you later. Thanks.